Hi, everyone. I'm very honored and pleased to deliver this presentation at Interplast 2021. It's entitled Polymers Recycling, Using the Past to Build Now a Better Future, and is essentially about transforming current and past plastic waste into building materials. I intend to share some data on circular economy, materials, post-consumed polymers as building materials, and some unpublished results of my research. I'm doctor in polymer science and technology, architect and urbanist, and I am working at the Queen's University of Belfast at the Polymers Processing Research Centre as an enterprise fellow. I would like to start bringing to your attention that we live in an economic model of infinite growth over a finite planet, which completely disregards the physical limits of the environment in its considerations. This situation calls for innovative and effective actions towards remedying the environmental damages, pollution, greenhouse gases emissions, wastage of energy and fresh water. In the last 5-6 years, the circular economy has gained visibility in media, influencing public opinion and policy making. Initiatives like optimizing the life cycle of industrialized products, enforcing the proper disposal of post-consumer materials, and attempts to reduce and rationalize the use and consumption of natural resources also contribute to achieving the circular economy goals. But as a consequence of pursuing a more sustainable way of conducting our lives, we saw society elect plastics as the enemy and declare a fierce war against it. Another visible effect of this so-called greener plastic-free ideal is the greenwashing phenomenon that has recently emerged. But the circular economy is not an error-proof science. Roland Geyer, in his 2016 article, Common Misconceptions About Recycling, has pointed out 4 consistent misconceptions that can be apprehended from the circular economy, which are the first, recycled material does not necessarily displace primary material one-to-one. First of all, because there's no engineering relationship or law of physics that requires the primary production of a material to decrease as we increase the recycling rates of this same material. The second one has to do with the recycling material multiple times is not necessarily better than recycling a material just once, because how much material is recycled each year will depend only on the supply and the demand of this same recycled material in the market. And in his third point, he says that the closed-loop recycling is not necessarily better than the open-loop recycling. In his example of the greenhouse gas benefit of re-refining used lubricant oil, repurposing this used oil into fuel gives an environmental benefit higher than closing the loop of this used oil back into lubricant oil. And his last point is that the distinction between closed and open loop is not useful to foster the circular economy, because the closed loop recycling does not guarantee high quality scrap. You see, the sum of these 4 points, I cannot deny that have been the source of many criticisms to my research, in which I have been standing for the point that it's best to develop building materials out of plastic waste because they have higher demand than closing the loop of each and every one of these polymers, if ever achieved the closed life cycle. Geyer concludes his point by stating These are the questions that we should be asking ourselves whenever we are thinking about recycling. What and how much resource is displaced by a recycling activity? Which are the uses of a recycled material with highest impact reduction potential? Which are the best level of reprocessing for this material? Increasing the value of a secondary resource increases its impact reduction potential, yes or no? And how can collection, recycling, and displacement rates be increased in a way that increases impact reduction potential? And when this recycling comes to plastics, things get a little bit more complicated. We here know that plastics is one of the two kinds of polymers existing, which are plastics and elastomers, or rubbers. And plastics are subdivided in two categories of thermoplastics and thermosets. Thermoplastics are these most well-known and most abundant in both in supermarket shelves and in our household waste. And thermosets materials like rubbers and these cross-linked plastics, they cannot be recycled the same way we recycle the thermoplastics. Therefore, we can safely say that no universal solution to tackle the plastic problem, the plastic recycling problem, will ever be achieved. The thing is, although plastics represent only 0.4% of the global consumed materials and just 0.7% of UK's waste generation, they still are the main target of environmentalists, waste managers, and circular economy discussions. One thing we all agree: post-consumed polymers must not be in the environment. Such a valuable material should be used as feedstock for producing new artifacts, preferably high-demand artifacts like construction materials. And we should treat these post-consumed plastics in a scientific fashion. And this can be done just by using what we already know about polymer science and technology. And we must be open to develop new techniques to expand this knowledge and maximize the environmental benefit of recycling plastic waste. As an architect, I have to bring to the discussion the construction industry. This is a very harmful activity that responds for the consumption of from 40 to 50% of all natural resources and consumes around the 43% of all energy produced in the planet. The bright side is that it's the second largest market for polymers and offers a wide range of applications where we can repurpose plastic waste into useful products. And it also requires lower standards than the packaging industry to achieve a marketable product. Actually, recycling plastics into building materials is not exactly a new idea. We can find in scientific literature some authors trying to transform plastic waste into building materials. Since 1991, for instance, it was hard to get images from the scientific papers, but for working in the Instituto de Macromoléculas Eloy Zamano for a long time, I had access to these samples of this blend of recycled PP and PE, which was patented as IMA wood in 1995 in Brazil. We can find on the internet some commercially available building products made of recycled plastics. This company in UK is manufacturing panels and roof sheets out of recycled multi-layered laminate plastics, which are considered of difficult recycling. There's also the production of plastic lumber, also in UK, made of post-industrial and post-consumer recycled plastics blend with a broad range of shapes and colors and aspects for their products. This brick that is produced in the Netherlands was originally created by an Indian architect and is 3D interlockable. And it's available for consultation on prices and shapes and colors. In Brazil, we have this very interesting wall tiles made of recycled PET, which is a pretty unusual way of shaping PET and using recycled PET, especially in Brazil, where the life cycle of PET is completely closed and you have market demand for this recycled resin. It's very unusual to find this kind of development, but from the environmental side, it's very, very interesting because plastics have a much lower environmental footprint than ceramic tiles, and their application on the walls are much simpler and does not require any cementitious mortar or water or anything, just contact glue. And as in general, they are also lighter and consume less energy to be manufactured and transported. So surely it fits all the checkbox for the sustainable choices in recycling a material. Talking about sustainable choices and going back to the impact reduction potential of Geyer, he says that identifying the options with the highest displacement potential should be the main guiding principle, not the number and type of recycling loops. Although I have learned about Roland Geyer just recently, since 2010, I had this idea of converting plastic waste into building materials for social housing projects in developing countries for low-income populations. And I am not alone nowadays, at least in this idea. I used to keep track of plastic bricks being developed around the world. And here at a glance, we have this most famous Colombian brick from Conceptus Plastics, where they mix plastic waste to some additives, which appears to be mainly something cementitious or concretitious. And they have this entire building technique because they deliver not only the brick, but also the pillars and the beams. So they have an entire building system that uses their material. Here again, that brick that is produced in the Netherlands or using 100% recycled plastics blend. And from India, I have these two examples. This one that's called silica plastic block produced by Renault machines, where they use foundry dust and sand waste in 80%, mixed to 20% of plastic waste, and produce, again, bricks for social housing projects, which the main aim is to use two sources of waste materials as inputs for producing new building products. And this one, Plastic Cube, produced by the Cube company, also from India, they just state that they use mixed plastic waste and remove plastics from the environment. But the goal is the same. This is pretty famous. It's from the US and Netherlands. It's called Biblock from a Bifusion company, where they use mixed plastic waste to produce these big blocks for building walls and installations in general. And I think this is recently the most famous one, the most famous brick, because this development became viral in several social networks, social media. It comes from Kenya, and there's a woman, an engineer, that is mixing recycled plastic with sand and producing these pavers, generating income and producing, once again, building products for people from low income. All these plastic bricks, they share the following characteristics. We see that the choice of plastics was made without any scientific criteria. And some of them use resins that are already tradable and already have a market value. It's very common also to notice that, except for that brick from the Netherlands, the plastics were not properly mixed in the molten state. But even that Dutch brick, Indian Dutch brick, its initial process, they didn't blend it properly. Only when the idea became a startup in the Netherlands that they obtained that more even aspect for their brick. But they still lack technical information for their brick, like compressive resistance and lifespan, etc. Another shared characteristic of all these bricks is that they seems to be molded by compression without any knowledge of polymer processing techniques to prevent defects and voids and have enhanced mechanical properties. This is one of the most important characteristics required by a brick. Science and technology usually is not applied to these developments, with materials resulting in homogeneous with poor processability and sometimes even degraded because they apply temperatures higher than the necessary to produce their bricks. And they do not understand the material on a molecular scale, meaning that they could if they understood, but as they don't, they cannot tailor the properties of their recycled plastics in the bricks to obtain the desired properties, mechanical properties mainly. And this one, I think, is the most significant one shared characteristic, that none of them is produced through a mass production thermoplastics techniques. And this is a key to succeeding in delivering a brick, because you need bricks by the thousands. So you do need a mass production technique to produce a plastic brick. In my research, I developed some interesting materials, like this synthetic paper made of recycled HDPE and sugarcane bagasse, or this other material aimed to produce bricks of recycled HDPE and coffee dregs, which ended up presenting odor absorbing properties. I also tried to mix recycled polypropylene with micronized demolition debris, still pursuing a fine material to work as a brick. And this is a very interesting development where I depolymerized Jeff's PET and combined it with castor oil to synthesize an alkyd resin. The case study of unpublished results that I want to show today here is an inevitable byproduct of plastics recycling companies that in Europe is known as sinking material. It comprises cross-linked polymers, rubbers, polyolefins, foams, and some composites, and is considered unrecyclable plastic. Here in Europe, a single company produces around 320 tons per month of sinking material and has to spend 40,000 euros per month to landfill this byproduct. But I gave a closer look to this material, in my spare time, and I have encountered very interesting findings. Using a scientific approach to this sinking material, I collected valid statistic samples and separated the unserviceable materials. Anything that was not polymer was removed, and I found around 1.5% of unserviceable materials, which was promising to the recycling of this material. And then I applied peer-reviewed processing found in literature of washing this material with water and neutral soap, reducing the particle size in a knife mill. Then I could assess the thermal and melt flow properties of the sinking material from PE separation and from PS separation. With this information, I could inject straight away dumbbell specimens and test its mechanical properties. The first idea was to use the sinking material as the base polymer for a composite to produce bricks. But soon I realized the broad range of applications that could use the sinking material, like tile spacers, paint trays, construction buckets, steel frame spacers, and wall plugs. At the Queen's University, where I'm working since 2019, I'm working in the development of plastic blends using recycled plastics for rotational molding. Basically, we make dry blends of rotational molding grade polyethylene, and not only plastic waste, but also other waste stream materials like natural fibers and inorganic material. And amongst this inorganic material, one of the best results was the blend with red mud, where we obtain an aspect of a very familiar material. This is the interesting thing of working with rotational molding. You can actually use the recycled plastic if you don't compound them before, and have a part that showcases the use of recycled plastics. Here, this green one, you see, it's here also. We used just PET micronized and mixed to virgin PE. And we showcase the use of a recycled material in the parts produced. After the expertise of the PPRC staff, we were able to reassemble traditional materials just by the application of natural fibers or inorganic residues in the blends of virgin PE. We were also able to previously emulate the end result of our rotational molded parts by preparing samples in an oven using the same temperature and times that would be used in the rotational molding cycle. All these developments we assessed through thermal properties, where we could check for the changes in the crystallinity of the blends, through melt flow rate of these materials, and checking one of the most important properties of rotational molded parts, that is the impact results of our parts. More recently, we've been studying blends of virgin recycled HDPE, ranging the recycled content from 10 to 100%. And we've been successful in preparing parts rotational molded of these blends. We've been trying not only dry blends, but also pre-compounded blends, and some testings were made using compatibilized blends that so far has resulted in interesting improvements in the impact property. We are also hopeful with the improvements achieved in the rotamoldability of blends containing high amounts of recycled plastics. And the next step is to explore alternative applications for the blocks, like exploring interventions in the original shape to transform it into storage box or into pet houses or outdoor furniture. As a conclusion, we can state that from the point of view of the demand and supply dynamics, transforming plastic waste into building materials is really a suitable solution. I may be biased for being an architect, but I do believe that the building industry provides a wide range of applications and requires lower standards for the use of recycled polymers and new products. And at last, recycled plastic reinforced with industrial waste materials will return better mechanical properties and provide increased sustainability, and will help us to clean the environment faster than approaches based on misconceptions. I would like to thank to the Engineering and Physical Sciences Research Council, to the PPRC staff, and to the Queen's University of Belfast for the support given during the conduction of these studies, and to Vanden Recycling and Van Veren Recycling for donating recycled plastics to these developments. If you are still here, these are my contact emails and the social medias where I can be easily reached. Thank you so much for your attention.